Yeah, okay, so real quick before we get back into the math, just a reminder announcement. So last week, I guess it was, I forgot exactly when, but I made an announcement about there's another survey that's out there, right? So y'all should have received an email from, I think it should appear to have been from me. It was actually from the people in NeuroInsight. But that survey in that link is available until the end of today. I think it goes through like right before midnight tonight. Again, that's worth 0.02 points of extra credit. So if you haven't done it already, please find a time to get that done today. Okay. All right. So back to the math. We're trying to solve first order systems of linear differential equations. We saw some ways to do that. It's fine. Kinda, right? I mean, the whole back solving thing's a lot of work. It is a lot of work. It's quite a pain to do it. But nevertheless, it's something that we can do. Trying to work around that, we defined this weird thing called a matrix exponential. Seems preposterous to raise e to the power of a matrix. But hey, at first glance, it's kind of ridiculous to raise e to the power of a complex number, isn't it? Right? We define that with Taylor series. So why not do the same with matrices? So we make this definition, compute, find to our amazement that the initial value problems that we're trying to solve are easy to solve if you allow yourself to use matrix exponentials. I mean, it's just jaw-dropping that it could be that simple. Right? All that really remains then is to figure out how do I evaluate a matrix exponential times some vector. That's what we don't really know how to do other than dealing with an infinite series, which, suboptimal. Okay. Furthermore, not only can you find a solution to an initial value problem, but you can find a fundamental set of solutions to your differential equation. By a simple method, pick any basis you like. It doesn't even matter. Any basis. Whatever. And just take those basis vectors, multiply by that same matrix exponential, and then bam, there you go. Fundamental set of solutions to your system. Right? So it's stunning how easy this problem seems like it is becoming. Except for, again, the sort of nagging, but we don't know how to evaluate matrix exponentials without infinite series, which again is a nightmare. Okay, next observation. There's a little bit of algebra that goes into this. It's not deep. It's pretty straightforward. I can show you if you're curious. It's nothing you really need to worry about. But here is a formula for multiplying a matrix exponential times a vector, which you'll notice, by the way, is how we find a fundamental set of solutions. So that's something we're interested in. And this is worth looking at then, except for the fact that, again, annoying infinite series of matrices. So what am I going to do with that? So the big idea for how to make all of this actually practical and not just pie in the sky dreams about magical matrix exponentials that we can't evaluate, right, is that I've got a foot in the door. If I can find vectors where what a minus lambda I does to that vector is easy to understand, right? If I can find vectors for which this is easy to understand, well then this entire infinite series will be easy to understand, which means that matrix exponential times that vector will be easy to understand, which means my fundamental set that I'm looking for will be easy to understand. And then we're in business. So that's the idea. The big idea is let's try to understand simple cases. What is a minus lambda I times a vector? What are the special vectors where that's easy to understand? Well, so the first obvious example is eigenvectors, right? If you're talking about an eigenvector, a minus lambda I times an eigenvector, always gives you 0. And that makes, of course, all of these terms in the infinite series disappear. And what we're left with then is a very compact formula for how to multiply e to the xa times an eigenvector. And I'm going to refer you now back to the big theorem from last time, or at some point last week, which was if you know all the eigenvectors, then all your solutions look like this. E to the lambda x, lambda being the eigenvalue, times those eigenvectors, and we just write them all down. Right? So in the case where the matrix is diagonalizable, this result is just kind of reproducing something that we already knew. Okay. So what we're going to try to do now is to extend, using this point of view, extend beyond what we've seen before, try to come up with other cases where a minus lambda I multiplies by a vector in a way that's easy to understand, therefore find new non-eigenvectors for which I can understand what this formula here gives me as a fundamental set of solutions. Okay. All right. So the big idea is I claim the Jordan basis is going to do that for us, Jordan basis. So I just want to point out why that is. It's not a deep calculation. It's a matter of kind of taking a new point of view on stuff we've already really done. So recall we know this thing called a Jordan a Jordan canonical form. Inside of Jordan canonical form are these basic Jordan blocks. Well, there's eigenvalue blocks inside of which are basic Jordan blocks. So let's look at a single basic Jordan block. Keep in mind, this is, we're representing, in this Jordan form, we're representing a linear transformation with respect to a basis. Right? And with respect to what basis? Well, the Jordan basis, or, a Jordan basis. Right? In a kind of a section 5.3 kind of sense, right? Matrices represent linear transformations. Now, a la section 5.3, how do matrices represent linear transformations? Well, the columns are telling you about the images of the basis vectors, right? So these basis vectors, look at their images by that linear transformation, write the results in that language. Those give you your columns. So applying that idea to this situation here, let's see here, can I fit, yeah, okay, cool. If I say that, okay, well, looking at this basic Jordan block corresponds to certain columns, those columns, etc. Those columns are telling me about the images of these basis vectors sitting inside of here. Now, that this is not the entire Jordan basis, right? We're just looking at one basic Jordan block. That basic Jordan block is just going to correspond to certain, kind of a subset inside of here of corresponding Jordan basis vectors, not the whole list of the Jordan basis. So anyway, these are the vectors that these columns are telling me about the images of. And specifically, what these columns are telling me are these equations. Now let's go through these kind of one at a time. This first equation is telling me this. There's a lambda in the diagonal position. The column this corresponds to is W1, so this is telling me about the image of W1, T of W1. Lambda in the diagonal position just means that it's lambda times that corresponding vector in the superscript basis, namely W1. Okay. Right. What about the rest of these columns? Well, the rest of these columns are telling me about the images of the rest of these vectors, W2 through WK, whatever. And there are these diagonal terms. Let's see here. I'll use yellow to represent these diagonal terms. Right? But then there's also these annoying, messing up the diagonalizability. There's those super diagonal terms, just above the diagonal terms. Right? And in the same way, those ones that I have in orange up there that are messing it up from being diagonalized, those are giving you these orange circled terms down here that are messing up our hope that these wi's might be eigenvectors. Okay. All right, so anyway, that's all just to kind of, interpreting a la section 5.3. So we have these equations, and now let's write all of that with respect to the standard basis. With respect to the standard basis, of course, T is just A, whatever our original A matrix is. So these equations become these equations with respect to the standard basis. And then we do one little quick little algebraic trick. I'm going to take these terms, throw them over to the other side of the equation, and I get this. And notice we got our wish. Now we've been in the weeds here thinking about this Jordan matrix for the last couple of minutes. So let me remind you what our wish was. Our wish, our hope, was to have vectors that have the feature that A minus lambda I times the vector is easy to understand. I wanted this to be easy to understand, so that would be easy to understand, so that I could make a convenient basis, a convenient fundamental set of solutions to my system. Right? So, is it the case now that A minus lambda I times these vectors is easy to understand? Well, yeah. Look, it's quite easy. This is telling us what A minus lambda I does when you multiply it by Jordan basis vectors. And it's a very simple story. What A minus lambda I does when you multiply it by Jordan basis vectors, it just takes you to the previous Jordan basis vector. Here, let me color code better. These equations here tell me that A minus lambda I times the Jordan basis vector just takes you to the previous Jordan basis vector. Yeah? Now, let's not get too far ahead of ourselves. It does that for these all but the first vectors in that list, corresponding to all but the first columns intersecting that Jordan block. Namely, the ones that have these annoying ones up there. Right? Thus giving us these annoying extra terms that therefore give us a 1 right there. Right? So it doesn't just keep happening forever. Eventually, you'll notice here, eventually you get to W1. What is W1? W1 is this first Jordan basis vector corresponding to that block. That vector, what does A minus lambda I do to it? Well, A minus lambda I sends it to 0. So we have, the end of the story is sort of inconsistent with what was happening before, but that's just an immediate consequence of how Jordan blocks work. Jordan blocks have these ones just above the diagonal, which means that the top left has nothing just above it, and therefore different algebra. Okay. All right. So let's put all of this together now. Again, we were looking at this equation. We now understand what A minus lambda I does to Jordan basis vectors. How can I use that to apply this sort of general formula specifically then to Jordan basis vectors? Here we go. Let's look at, here it is, just recopied for convenience. There's our initial equation. Let's consider what happens when I apply this to a Jordan basis vector, Wi. Right? Well, Wi being that vector. First thing that happens is I've got to multiply A minus lambda I times that, and of course that gives me Wi minus 1. Now, the next thing that happens, over here, I've got A minus lambda I squared. That's multiplying by whatever Jordan basis vector we're looking at. What does a minus lambda I squared do? Well, let's go over here to our diagram. A minus lambda I squared, well, whichever Jordan basis vector we're looking at, we're multiplying by a minus lambda I, and then we're multiplying by a minus lambda I again. So we're moving to the previous Jordan basis vector, and then we're moving to the previous before that. In other words, if you were looking at Wi, it takes you to Wi minus 2. It just shifts you back 2 steps in this little diagram. So, Wi minus 2. Et cetera, et cetera, et cetera. Continues. So going back over here to this formula, eventually we'll be multiplying by a minus lambda I cubed, and then a minus lambda I to the 4th, and then to the 5th, etc. And eventually we're going to get W1, and then after that, notice we get 0. Right? So you'll see that at the end of the rewrite of the formula here. There's this, however many factors of a minus lambda I, that times v gives you W1, and then all the terms beyond that just give you 0. So the lovely little result we have then is that if you're looking at a Jordan basis vector, right, and you're multiplying e to the xa times a Jordan basis vector, you take this formula here, where the pattern is, you start with that same Jordan basis vector, and then you just go backwards one step at a time through the list till you get to the eigenvector for that basic Jordan block, and then you stop. You don't go any further than that because, of course, in the sequence up here, everything after that is all zeros. Lots of details in that calculation, aren't there? So that's this would be a good section of the lecture to go to the YouTube channel and rewind and do a lot of pausing and thinking and rewind again and listen to the second time, etc. Take all the time you need, but there's a lot of details to follow here, and so give yourself time to absorb that. Okay, now let's use this to solve a problem. Recall we've already solved this problem here. We did this before break. At great inconvenience, I'll point out. Right? This is the one where we said, well, we've got this non-diagonalizable matrix, coefficient matrix for our system. We Jordanize by hook or by crook. Right? We were given, in this case, this Jordanization. And then you do the change of coordinates, and the punchline is you end up with a system where these are your coefficients. And you go through and you do the whole back solving thing, which was such a pain, right? Lots of algebra in there. And then rewrite this, rewrite it from one form into another form, and multiply by the P matrix, and out comes your answers after about 3 pages of algebra. Yikes. Okay, so let's do it again. Notice that this, being our Jordan matrix, represents the transformation in V language. Therefore, this matrix over here is change of basis V to S. Therefore, this Jordan basis consists of those columns. We've got ourselves a Jordan basis. And once we know the Jordan basis, we immediately know that I can take those Jordan basis vectors and just multiply by the matrix exponential to get this fundamental set of solutions here. Again, this is kind of ivory tower abstraction of it works, and yet I don't know how to evaluate these things immediately. Right? What in the world is a matrix exponential times a vector? But using the formula above, matrix exponential times Jordan basis vectors, critically, we do know that these are Jordan basis vectors. I can rewrite with that formula. And that's all I do in this last step, is just rewrite with that formula. And it's pretty much done. Isn't that convenient? Last little details. Don't forget what these Jordan basis vectors are. So these Jordan basis vectors here are those given above, and if you take those Jordan basis vectors and plug in and multiply as this suggests, a little bit of algebra of doing there, but punchline, you get this as your solutions. And now I'd like to encourage y'all to flip back in your notes to the appropriate page, earlier in this section of lecture notes, and this is the exact same solution that we got after 3 pages of back solving and rewriting and all of that nonsense. So, this is a lot easier. How's everybody doing? Any questions? Everybody happy? Almost a little too good to be true, isn't it? So I do want to encourage y'all, make sure to don't forget that what we're doing here with matrix exponentials is really just kind of a shortcut around, the fundamental idea that's really important is that we're taking a new point of view on the linear transformation. Right? The linear transformation was initially given in standard basis language as that A matrix up there. And the thing that makes the matrix exponential work is the exact same thing that made the back solving work, namely the realization that the standard basis is the wrong basis. You shouldn't be thinking about this transformation with respect to the standard basis. That's rigid and awkward. Right? We should be thinking about this problem with respect to the Jordan basis. So with the back solving thing, we just use that point of view to turn it into a different system. With this point of view, we use it into a tool to evaluate matrix exponentials. So, whatever. Right? I mean, that's the superficial details. The big point is still the change of coordinates, change of variables, realizing that the V basis is better than the S basis. Yeah?
Where does the 1.5 x squared come from in the third?
Yeah, sure. Okay, so I kind of glossed over the mechanics there. Let me do that. So let's go up to here. Here's our formula, right? Which, just as a reminder, came from here. Right? By the way, if you keep tracing it back, ultimately this x squared over 2 came from this formula, but that came from this formula. Where did this come from? Well, this came from the definition of matrix exponentials way back when. Right? And where did that come from? Well, ultimately it came from the fact that that was our formula for Taylor series. Does that make sense?
Yes.
Cool. Anybody? Great question. Anybody else? All right. Alrighty. That's a neat method. So I want to encourage y'all to, use this method when the opportunity permits. But again, don't hang your hat entirely on this. I think that the whole point of view of changing variables from the y variables to the z variables, and how the P matrix then converts from the Z solutions back to the Y solutions. That's a really important point of view. Ultimately, that's what you're doing here. This is just a shortcut around the details. Okay. Right. I'll show you one more example of this. And this is just an example to illustrate the importance of a detail that we talked about here, which was that we were going to look at a single Jordan block. Here. Right? It is for a single Jordan block. Not the whole Jordan basis, just the part of the Jordan basis corresponding to a single Jordan block. And it is this diagram here that allows us to rewrite the formula corresponds to just the basis vectors in a single Jordan block. Right? So you've got to stop when you get to the corresponding first vector in that list. Namely, you stop when you get to that eigenvector there. So this first example, just to keep life simple, you'll notice there was only one single Jordan block. And again, that's a good starter example to see how the sort of the mechanics work. But this conceals the fact that not every matrix will have just a single Jordan block. So what do you do in a case like this, where we have, well, there's a Jordan block, but then here's another Jordan block, and here's now a third Jordan block. Now, how does this matrix exponential method work out here? Well, recall, columns tell us about images of basis vectors. This first Jordan block corresponds to 2 columns and therefore tells us about 2 basis vectors, and therefore we get this diagram corresponding to those first two basis vectors. Likewise, the second Jordan block, columns 3 and 4, telling us about Jordan basis vectors 3 and 4, and we have this diagram pertaining to vectors 3 and 4. And then likewise, this last diagram. So when we write out the matrix exponentials, keep in mind it remains the case that this is your remains the case that this is your fundamental set of solutions. Right? All you're doing is multiplying the matrix exponential times your basis vectors. It's just the evaluation of these matrix exponential times basis vectors that's going to be a little bit different. And in this case, here we go. Evaluating the matrix exponentials on V1 and V2 gives me those. Just for emphasis, let me write it down again. This is e to the xa V1, and this is e to the xa V2. So 2 examples of us using the formula on the previous page. Right? But then, when you switch over to V3 and V4, we're going to get, we have this different diagram, and therefore these evaluate differently. Right? So this is, this is e to the xa V3, and this is e to the xa V4. Okay, so common mistake that students will make is when they're evaluating e to the xa times V3 here, they'll see the V3, and they'll look at this formula over here, and they'll see, okay, so you just keep dropping that subscript, and you just keep dropping that subscript till you get to 1, misinterpreting it, thinking that the point is about the subscript. It's not about the subscript. It's about the fact that this is the first basis vector corresponding to that block. Right? It's not about the subscript being 1. So over here, corresponding to that green block, V3 is the first basis vector corresponding to that block. So both of these, we stop when we get to V3. Okay. And then likewise for the yellow block, we get that solution. Okay. All right, so something to be careful about. All righty. Yeah. So I guess one last quick pause for questions before we go on to the next section. Everybody feeling pretty good about these matrix exponentials? Okay. So, following the pattern, by the way, I mean, let's think back to Chapter 4. What did we do in Chapter 4? We spent one section talking about kind of theorems and setup and strategy. And then we had some discussion about, well, how do you solve homogeneous equations? And then after that, we talked about non-homogeneous equations. Well, here in Chapter 6, we spent a section talking about, theorems and setup and strategy. That's 6.1. And then we spent, in this case, 2 sections talking about homogeneous systems. So we talked in 6.2, we talked about the diagonalizable homogeneous. And in section 6.3, we talked about the non-diagonalizable homogeneous. And so following the pattern, here we are going to talk about non-homogeneous solutions. So, when you have an extra term over here, making it non-homogeneous, how do you find that particular solution? Right? We know we only need to find just one particular solution. How do you find it? I am going to do a little bit of jumping around at this point. We are, as you've, I'm sure, noticed, getting very close to the end of the semester. As I'm sure you have also probably noticed, we're not exactly up to the schedule, on the lecture schedule. We're a few pages behind. So this is pretty routinely the case. I always factor in that we've got some flexibility at the end of the semester. A fair amount of the last, 20 or 30 pages of lecture notes are non-critical. So what I'm going to do is I'm going to jump over some non-critical things to get to what I think is more important. We're going to talk about for Math 216's purposes, some of the more critical things. And then, time permitting, I'll get to some of the non-critical things, if we can. And if we don't, it's fine. It's not a big deal. So I'm going to kind of gloss very quickly over the next few pages here. For the moment, just don't worry about it. Yeah?
Is the stuff that we covered today going to be on Wednesdays?
No. So if I remember correctly, and you know what, let me not trust my own memory. That's dangerous. Let me come over here to the lecture schedule. Let's see here, 216 lecture schedule. Let's see here. Yeah. So the exam 3 you see here in green, right? You see also over here color coded in green the last section of 6.2. So 6.2 was the diagonalizable case. So all the stuff that we did today is from 6.3 and beyond. So the stuff from today is not fair game for the midterm exam. But all the stuff from today and likewise all the stuff from Friday will all be fair game for the final exam. And by the way, while we're on that topic, let me go ahead and throw another idea out there, which is that the stuff from today and Friday is fair game material for the final exam, which will not have appeared on any midterm. And so you should expect that to, on the final exam, have heavier focus, just to kind of even things out course-wise, right? So roughly speaking, over the entire value of the course, I want all the topics to be or ballpark equally weighted. Not for the midterm, but yes for the final. Yeah, great. Okay. Right. So let me skip down here to, this is page 287. There we go. On page 287, we have a formula, and we'll get to talking about why this is true, time permitting, maybe Friday, if we can. You want to find a particular solution? Cool. There's a formula for it. It's very convenient. I say convenient. That's an abuse of the term. Notice what there is going on in here. This M, remember, that's our fundamental solution matrix. So it's a matrix. Right? Notice here, then, we have to invert that matrix. Right? So that's inconvenient. We don't like that. Notice as well, I'm going to have to do an integral here. And furthermore, this isn't just an integral. This is an integral of a vector of functions, right? We've got a matrix times a vector. This integrand is a vector. So this isn't just one integral. This is in separate integrals. So, not that great. It's pretty inconvenient very often. And I just want to show you how inconvenient it can be in this example. We're not going to go through the details. I'm just going to hit the highlights. But so you see here a non-homogeneous equation. You can look at the homogeneous part. Recall these are the solutions. I like to reuse this same example over and over again because, we all know how to find those solutions. There they are in this case. Thus, we have this matrix. That matrix you have to invert. Having inverted it, you've got to multiply by the G vector, right? And that's, so you got to multiply that out, no big deal, but you get that vector, and that you then have to take an integral of. So we're taking an integral then of these two functions here, both of which require integration by parts, and bummer. But that's, you can do that. I mean, it's just details, but it's quite a bit of details to get to that antiderivative. Of course, even then, we're still not quite done. Remember, the formula is that you take that antiderivative, and then you have to multiply back times the M matrix. And so you can see it's a kind of a clunky process that results in an answer. Yeah, everybody good? We'll talk more about this method again if time permits. But I want you all to see that it's there and that it's not particularly appealing. Okay. Another quick example, and just, I think this is a good thing to spend a moment on. We had this idea back in Chapter 4 that when you have sines and cosines that promise to create inconvenience, you can instead look at the associated complex equation. Notice that the real part of that is that. And we can argue then that the real part of this z is the solution y that we're looking for. Right? So you can turn an equation that involves cosines, and that's going to be that's going to be hard to do because let me show you how hard it is to deal with this. Given that you have a cosine in here, let's see what would happen if instead of x's, what if we had a bunch of cosines? Let's see here. Where am I? Yeah. Then we'd have cosines. These are even harder integrals. Right? Y'all remember how to do integrals of trig functions times exponentials? You have to integrate by part twice and then do a little switcheroo algebra trick. It's a pain, right? So that would be inconvenient. But notice that if instead we look at this associated complex equation, okay, it's complex, and that's, all else being equal, I suppose not as good. But look at the integral that you end up having to do. You end up having to do an integral of, what is in fact just a bunch of exponentials. And integrals of exponentials are easy. They're among the easiest integrals out there. Right? Right up there with polynomials on easy to integrate. So it's a big win. So if you find yourself in a situation like this one where you've got trig functions, think about instead looking at the associated complex equation. Okay, all right. And then of course, look, there is some complex arithmetic that you've got to deal with, right? You've got to convert that into that, but it's just arithmetic. And all else being equal, I would take complex arithmetic over nasty integration by parts every time. Okay. All right. So I want to get now to the what I think is really the more important method for you all to understand, and it's really a lot like what we saw back in Chapter 4, Section 4.3, which we called undetermined coefficients. Y'all remember undetermined coefficients? You guess the form of the solution based on kind of appearances. And then, you throw in some fudge factors and solve for your fudge factors, right? That's the big idea. So, the same thing is going to work pretty well in this circumstance. So, here we go. Let's suppose that our non-homogeneous right-hand side term is that. What would you guess the form of your particular solution would be? What kind of odds would you put on this particular solution y having, cosecants in it? I mean, probably not. Right? Come on. We need terms that are going to make stuff like this show up in the process of taking derivatives. And what makes stuff like that show up? Well, stuff that looks kind of like this that we have here. So we're going to guess, based on the form of this, we're going to guess that our solution Looks kind of like that. Which, for convenience, I'm going to rewrite like that. So, having formed our guess, notice we have these fudge factors. I mean, I don't know what this A vector is going to be. I don't know what that B vector is going to be. I just feel like it should have this form. We take that guess, we plug it into there, we see what pops out, namely this. That's the equation I need to solve. I need this to be true for all values of x. If it's true for all values of x, then I need like powers of x to work out simultaneously. So specifically, let's look at the no x's terms. Now let's look at the terms that do have x's. Right, you separate that blue equation into these two equations. Now I just need to find a solution to these two equations. And here is where it becomes, every question is going to be a little bit different. How do you go about solving this algebra? We got to think strategically, right? Don't try to solve for the A vector yet because we don't know the B vector. But we can solve for the B vector because I know everything else in this equation. So solve for B first. And once you know B, then you can solve for A there. How we doing? Anybody see the idea? A little bit of algebra, a little bit of inconvenience, but not that bad. Pretty straightforward. And I think if you look at the comparison here, just for dramatic effect, let's look at there's the algebra that we had to do on this one. You got to plug in a form into an equation, take a derivative. Yeah, you have to use the product rule. Okay, but then let's see. Oh wait, do you? No, you don't even have to use the product rule. So it's some really easy derivatives, and then you get two easy vector equations. Alternatively, you could instead do all of this nonsense, which involves ugly integration by parts and more algebra. And here's the other weird thing. Exponentials all over the place. Isn't that strange? Look, you look up at the top equation. The top equation doesn't have any exponentials in it. The answer doesn't have any exponentials in it either. And yet the solution to get from the easy question to the easy answer is just chock full of exponentials. That seems a little strange. It seems a little wrong, strategically wrong, if nothing else. This is, as it should be. We have an easy question involving just, linear terms in x. And our answer is, come on, just linear-like terms and linear and constant terms in x. And our solution also easy, constant, and linear terms in x. Okay. So this is kind of the big idea for how we find particular solutions. Most of the time, something like this is going to work. I mean, it's hard to quantify when I say most, but very often something like this is going to work. Now, you might wonder if there is a big theorem coming. Remember back in section 4.3, we did a few examples kind of like this, where we looked at the form, we made a reasonable guess, we solved for our coefficients, and we got answers. Having done a few of those examples, we then stated this great big theorem that says, look, in this broad category of cases, huge numbers of cases of right-hand side, here's exactly what you should guess. So are we going to have such a theorem here? And sadly, no, we're not. Things are a little weirder when you're looking at these this sort of the vector version of this situation, and it's prohibitively difficult to phrase a theorem that would actually be true that works in such broad generality. So I'm going to show you the next example. I'm going to show you is just kind of points in the direction of that sort of a weirdness. So So let's suppose we wanted to find a particular solution to that equation. First order, linear, non-homogeneous. We take our non-homogeneous right-hand side. We ask, based on the form, what would we guess? It seems like a likely candidate solution. And, well, look, something along that same form, right? I mean, if I have something like this, e to the rx times some vector, multiplying it by a matrix will give me e to the rx times some vector. Taking its derivative will give me e to the rx times some vector. When I subtract those two vectors, I'm going to get some vector, and you can see how it seems kind of plausible that I ought to be able to make that vector v by fiddling around with it accordingly. So we take this guess, plug it in, see what our equation becomes, and our equation turns into this. Can I solve that equation? Again, given that the v is a given for the problem. If I know v, can I solve for a? A is what I want to know. Can I solve for that a? Well, sure. Right? Just, you're going to have to invert this matrix. And then, bam, there's your a. So, fine, no problem. Unless, of course, and here you start to see, how things can get a little weird sometimes. It is possible that this matrix might not be invertible. Right? So what do you do if a minus ri is not invertible? Let's see, how else would I say that? If a minus ri is singular, let's see, how else might I say that? If that coefficient in the exponent up there is an eigenvalue of the coefficient matrix. All right, what a weird little coincidence to pop up. But if R is an eigenvalue of that coefficient matrix, then this matrix is not invertible, and therefore I cannot definitively solve for A by playing the usual game. And I might get lucky. There might be a solution anyway, but might not work. Okay. Alrighty. Is everybody on board so far? Okay, so what do you do if that's the case? And here's an explicit example. Now, y'all will recognize, of course, our old friend, this matrix. Hopefully, y'all will remember. Or if you don't, easy to check. This is this is an eigenvalue for that matrix. So this is the scenario that we were worried about above. If we were to take, this form right here, if I were to take that and plug in and see what happens, I would have to invert a non-invertible matrix and, of course, crash and burn, right? So what do we do instead? Now, again, we don't have that big theorem to fall back on. I can't just go to the equivalent of section 4.3 and say, well, then you count the multiplicity of the blah blah blah. It doesn't work out like that. What I'm going to do is I'm going to add in a hopeful extra term. I'm going to add in that extra term. The idea is that even though that's not the form over here, when I put that in there and take its derivative, in taking that derivative, one of the terms will look like that. And so the hope is, with fingers crossed, the hope is that this extra term in the prospective solution will allow us to, get a foot in the door in dealing with that right-hand side that previously we weren't able to deal with. So with that in mind, let's take this hopeful form of solution. Let's pop that into the equation, and a bunch of little algebra and calculus to do. You've got to take the various derivatives. Here you do have a product rule, and you plug it all in, and the equation turns into this. And now you have another little algebra problem to solve. Notice that I have separated out the like powers of x. So here's the coefficients of the x to the 1 Here are the coefficients of x to the 0. If I want this expression to always be 0, the 0 vector, then I need for both that to be 0 and for this other thing that I have up in yellow to be 0, and therefore for this equation here to be true. So I need for the blue equation to be true, and I need the yellow equation to be true. And now notice we find ourselves in a situation not terribly different from what we saw over here. Here, I needed for this to be true and for that to be true, and you make the right choice, go in the correct order, and solve your equations. And it's not that different here. Two equations, make the right choice, go in the right order. There is some twists that we're going to talk about next time, but pretty much it's just a matter of solving these equations to get your answer. Okay, good stopping point. See y'all on, see you Wednesday for the midterm, and then see you on Friday for the rest of this story.